Yeah, it's my great pleasure to be here, and thanks Yujie for the introduction, and also Masashi for the very kind invitation. Today, I'm going to talk about our recent work on uncertainty quantification for large language model-based survey simulations. Um, here's an outline of the talk. I'm going to first introduce the basic setup of the problem. What do we mean by using large language model to simulate surveys? And then talk about the key idea behind our method and convince you of its theoretical guarantees. Then we will go to a few nice interpretations, providing more insights and intuitions behind this method. And finally, we'll show through a few numerical experiments to illustrate the efficacy. So let's start with the basic motivating example. What are surveys? Well, surveys are very commonly used tool to collect data and inform decision making, right? So they have very wide applications in there's a variety of fields. Just to name a few, in marketing, people are interested in learning about the customer preferences and also the market trends, etc. What is going on, right? And in social science, especially computational social science, people wanted to gather public opinion toward common issues and learn people's behavior, right? Strategic behavior, collaborative, etc. And also the impact of certain policies. Right? So in education, especially online education, people would like to learn about student feedback, how much student can understand certain abstract materials, right? Or if they design, let's say, a new test question, would that be too difficult for this group of students or too easy, etc. And also, of course, there's a lot of other applications, including healthcare, government, you name it. Right? So surveys are just ubiquitous, and they usually follow this general pipeline. So at the beginning, you need to prepare the survey. That consists of designing questions and selecting the population of interest, etc. Right? And after the preparation, you will collect the data. That means among the population of interest, you distribute your survey and collect the responses. Okay, and once the data is in, then you apply standard statistical analytics. Right, there are lots of software packages for to estimate the error, and finally you will make a. Is there a question? Oh, yeah, and finally you will present the results and to inform decision making. Right, and along this whole pipeline, the second step, that's the data collection, is the most time consuming, and also it's the most expensive part, right? So now it's of great interest to facilitate this second step, right? How can we collect the data more efficiently? That's a key question. So nowadays, the large language models have been widely used in many different areas, and people have been thinking, can we use large language model to gather simulated survey responses, right? So it's pretty simple. You have a large language model, you just query it with certain user profile and certain questions and ask the language model to mimic the person and respond to your question. So that's a key idea. And this has been already widely studied in many different areas, so including economics, computational social science experiments, okay, and also market research, education, etc. Yeah, there's nothing is completely new under the sun, so there have been lots of existing work. So this is how it usually works. So in the traditional survey, you start with a bunch of real people and you hand out your questionnaire, you collect the responses. So in the simplest scenario, your questions are just yes or no questions. Then you will get a lot of yes or no answers from those people. Okay. And when you use the large language models, so instead of querying real people, you start with a database of user profiles, right? So each document or each row in your data sheet, spreadsheet, could correspond to one person of interest. And then, so you randomly select one profile from your database and also, and then hand it over to the large language model. So denoted by this robot, right? You choose a profile and choose a question, hand it to the large language model, and then collect the response. So in doing so, you can also get a bunch of responses, right? And this is the synthetic data. So that's the whole pipeline. So just to illustrate the idea here, one example is how you conduct public opinion survey. So suppose I want to use the language model to do this. So first, I'm interested in one particular person with this type of profile. There's region where this person is living in, the age of the person, education, income, etc. You can collect lots of if you have a database, you can just randomly sample one user profile. And then, so you ask the language model to impersonate such a real human, and then respond to this question in the blue box. Right? The question asks, how much do you think wages and incomes are contributing to your opinion about the economy? Right? So that's a social opinion question. And they can answer. So in this, this is an example from the Pew Research Institute. So it's a multiple choice question from a great deal to not at all. And of course, there's a refuse to answer option. So if you hand it to a real person, they will choose one out of the 5. And you can also ask the language model to pretend being the person with such a user profile and respond, right? So typically, the language model will first conduct some, some reasoning, some chain of thought. So they will say, okay, so suppose I'm this type of person, then what should I do? What's going to be my behavior? So you will see a few paragraphs of reasoning, and then finally, the language model will jump to an answer. Yeah, and if you query the language model a few times, even with exactly the same profile, you may still get different answers because of this randomness. Yeah, so that's how people usually do simulated survey in this way. And of course, another example is in education. So here, I want to understand how how much can let's say elementary school or middle school students understand abstract mathematical concepts. So I will ask the language model to pretend being a student of certain age in a certain school district. You can also input a few past grades in relevant courses, etc. And then you ask the language model, if you were this student, then how would you respond to this? How would you answer this, right? If you multiply a square number by 9, you get a square number. Is this always true, or etc. Right? So of course we know you should choose A, but for let's say an average elementary school student of certain features, they may or may not be able to answer it correctly, right? So and then the language model will give some thoughts, and then eventually jump to one answer. Yeah, one plausible answer, right? So this is it's very important task for instruction, because teachers definitely want to learn how much the students can understand. And so if they design a question like this, and suppose they want to use it for their midterm or final exam, so at first they want to preemptively assess the difficulty of such question. If no student can answer it, then maybe it's too difficult. If everyone can answer it, then it's too simple. So in either case, it's not the best design of the question, right? And here is also a type of different task than the very commonly used approach, because if you look at those lots of existing study in large language models, they want to fine-tune the model to achieve superhuman behavior. Let's say they are much smarter than even average undergrad student or graduate student in solving math questions. Yeah, that's the commonly used benchmark. You want it to achieve higher accuracy than the real students. But in this task I just mentioned, it's not about achieving superhuman behavior, but just to the right amount, right? You just want to mimic what the actual students can perform. Yeah, so that you can view it as an education simulator. And then you can use it to better optimize your instruction practice, etc. So yeah, I myself find this pretty interesting field. So just to summarize, when you use large language model to simulate survey, you query it to get responses, and there are very clear pros and cons. First of all, it's much cheaper than the real human data, and of course, much faster to collect. So you just type something, through the API interaction with the language model, and in 1 or 2 seconds, or at most a few seconds, you can get a response, and it's also pretty cheap, right? But the con, right, this drawback is also pretty clear. Because there's an unknown misalignment between the large language model and humans. You cannot fully trust the simulated behavior or predicted behavior of the language model because it's not a perfect replicate of the real human, right? So that's, yes.
I'll go back to the previous page.
Yeah.
For example, when you want to do this survey, you don't directly ask some like preliminary school students. You ask some smart adult, like some researcher like 40 years old.
Okay.
But you ask them in the same way you ask large language model, like pretend that you are some like a 9 years old student.
Yeah.
Then have you ever considered or have you ever checked whether this is aligned?
Yeah, that's a perfect question. So around 10 or 15 years ago, a lot of people were actually doing that because Amazon launched a product named MTurk. Yeah, that's an MTurk product. So they basically, it's a cross-sourcing effort. You can upload your task. Let's say you want to annotate a bunch of images, or you want to collect survey to a certain questionnaire. So whatever task you submit it, you upload it to Amazon's MTurk system, and then the MTurk will, they have people around the world that are, let's say in their spare time, they want to get some money, and they can help you do it. So around that time, around 2008. People have been using the MTurk as such simulator, and you can imagine those people serving, participating in a cross-sourcing effort were actually 30-year-old or 40-year-old adults. But if you hand such question to them, you can ask them to pretend, as if they are a pupil or etc. Yeah, people around that time people were doing that and also understanding the potential bias.
Okay.
Yeah.
I think for some purpose, for example, education, maybe this works. But if you consider some other examples you listed in the beginning of application like marketing, like you ask a Chinese, pretend you are Japanese, and whether BYD should go to the Japanese the market, maybe you will also get very serious bias.
Exactly. Even for the large language model, because it's trained on some type of data from the internet, it also has uneven coverage over different aspects and different.
More serious, right? But the bias come from some other source. It's not the fault of large language model.
Yes.
It's like the data because the data are created by humans.
That's right. So that's all of those questions can be tackled in using our method. Yeah, just stay tuned. Yeah, but those are definitely great questions. Okay. Yeah, we'll come back to that point because all of those questions can be summarized as some misalignment. It's not misalignment between LM and humans, but in your example, it's misalignment between the target population of interest and the actual respondents to your survey, right? So we'll have a unified umbrella to cover all of them. Okay, so over the past 2 years or so, people have been understanding this, trying to understand this misalignment by developing a few similarity and discrepancy metrics. Right? They want to measure such alignment using some optimal transport distance or divergence, etc. Yeah. Okay, but so we will take a different approach. We will not just use those metrics to gauge the discrepancy, but also we will provide a more operational, some more operational guidance. So we seek to answer these questions, very operational and practical. First of all, how many synthetic responses should one generate? Because you have a language model, and in principle, if you don't care about time or money, you just query it as many times as you like. But we'll see, sometimes less can be more. Yeah, because if your data is biased, then there's no point, there's no benefit in collecting too many samples, because that can lead to severely biased answer. And of course, how do we analyze the errors? So these are the key questions we seek to answer. So now let's go to the key method and theory. So let's start with a toy example. Suppose you are just interested in estimating some population proportion. Right? You want to estimate the proportion P of people with a certain feature. Let's say how many people will drink coffee every day. Right? That could be some feature. You can just define a feature, or how many people would approve this or would prefer A to B. So it's just a simple proportion of interest. And if you randomly sample real humans from your population of interest, then for each human, right, for each sample, you will get a Bernoulli random variable with parameter P. Because if this population is unbiased, then this is the correct number. And then you use language model, you will get synthetic response. Those are still yes or no answers, but perhaps it's from a different distribution. This is a Bernoulli distribution parameter Q. And generally, P and Q are different because of the misalignment. So your point estimate constructed from the synthetic data can be biased. And if you want to quantify the error, you construct a confidence interval that may not have the valid coverage. Yeah. So that's the issue, because P and Q are generally different. So let's see through this example. Now, imagine you have a data stream. So you have language model and keep collecting data from it. So from sample 0, from the first sample to up to 200 samples. Okay, and imagine for your question, the actual population fraction is 30%, but if you get answer from the language model, then it's biased. It's centered around 50%. So you keep collecting data, and upon collecting a bunch of data, you can construct a point estimate, which is your empirical fraction. And then along the way, you will get this blue solid line. This blue solid line represents your point estimate over time. So eventually, it will convert to 0.5. That is the bias distribution given by your LM. So you can imagine the large language model actually implicitly defines a synthetic or imaginary population, right? And the true answer is 30%. So you see, you can use standard statistical method to construct a confidence interval to perform the error bar. But as time goes by, the error bar will shrink, right? And that will shrink toward a round target. That's a 0.5. It's not what you want. If you really collect 200 samples and construct an error bar, this error bar is not really meaningful, right? Whereas if you collect too few samples, let's say only 5 samples or so, your error bar is too wide, and also there's no good, right? But in this example, if you collect around 20 samples or so, and then construct your error bar, then your error bar still has it still managed to cover the real one. So it seems the sample size.
The error bar just by running experiments many times.
Yeah, you can do that. So in this example, I used the Hofding bound to construct the error bar because that's non-symptotic. But you can also run multiple times and get error bar. Yes, yeah, that's related to the bootstrap idea. Right. Either is fine. We'll talk about that. Right. So in this example, it seems about 20 is the right amount of samples. Right. It will not make you overly confident, and also it has a minimum error bar. Right. So now we want to select a good sample size so that you can still maintain the good coverage while not being overly conservative. Okay. So in this example, we can see the key takeaway is that less can be more. There's generally no need to simulate too many times, because if your data is biased, simulating too many times will just mislead you, right? And that also incurs high computational cost and give you an overly short, invalid confidence interval that results in overconfidence. Right? Your error bar is not a real error bar. So now in our study, we seek to choose an optimal sample size, a sweet spot in between. So theoretically, in the example I just showed you, if you can get some sense of the optimal sample size. So in the sense that if your real proportion is P and your synthetic proportion is Q, then roughly speaking, your optimal sample size is inversely proportional to the KL divergence between two Bernoulli distributions, P and Q. Yeah, you can compute this theoretically, but in practice, right, you never know P or Q. So you cannot really use this formula to select the sample size. Yeah. Yes. Yeah.
Oh, sorry. And not maybe I do also maybe I do something about why more sample is not that good. Is a good choice. We have a more sample. We have a better estimation of the Q. So
that's right. You have a better estimation of the Q, but Q is different from P.
Yeah.
So and you're
then
yeah
to distinguish the two that if there are two distributions.
Yeah, so you want to estimate P, or you want to get some insight about P.
Okay.
And if you're not targeting Q,
Okay.
you want to yeah, a great question. Yeah, your goal is to estimate the real proportion P. Yeah, you're not interested in Q. So if you have some estimate of Q, but with a wide error bar that can cover P, then that's good. Yeah, because eventually
Wide error bar, so we do not know where P is. So it's
you only know the P is within that interval.
Okay.
Yeah.
It could be maybe, for example, in previous figure.
Opposite direction, right?
Yeah, it's
Yeah, that could be possible.
Yeah.
This one doesn't tell you the direction.
Yeah.
That's right. But in general, if you want to make it work for any black box large language model, perhaps this is the only thing you can do.
Oh,
Yeah. In some cases, you can do better. Yeah, indeed.
Survey is the just maybe my personal opinion, because in many cases it's about inform the downstream decision making. So if you are not overconfident, you feel that maybe then you will try to do more survey. Like for example, you first use the large language model to simulate it, and then you will do the real survey.
Yep.
But if you are overconfident, you say, oh, we are ready to make the decision, and then you will make the wrong decision, especially in marketing.
Yeah.
Right.
That's perfect explanation. Yeah, that's also what we have been thinking. Yeah, indeed. So yeah.
Can you use any like data simulation technique to kind of fit element to the real world data? That's often done in scientific simulation.
Right. So currently, we focus on, we just handle a given LM, and let's say you have a black box ChatGPT or something.
You can tune prompt.
That's right. So the next step would be, if you have some real survey response and synthetic, can you fine tune your language model a little bit to make it better aligned with the people? Yeah, that's right. Yes. Yeah, and indeed, this error bar can inform the downstream task, because the scenario you mentioned is precisely what I've been thinking about. You should view this simulated survey as a preemptive assessment. You want to understand what's the fraction of people that are in favor of this, right? So, or they prefer A over B. And if you are already very confident about that answer, then you may directly jump to decision. If this method give you a wide error bar, that means you can still go back to the real people and get, that's exactly the case. Yeah. Okay. So to summarize, we want to select some sample size, and here's the key the overview of our approach. So we will first collect survey data from real humans, like the Pew Research Institute and some online platform. So there have been existing database, and so there are a bunch of survey questions, and for each question there are a lot of real human responses, and given those questions, you can replicate the study using LLM, and then compare your synthetic data with the real data to somehow learn the discrepancy and select a sample size. Yeah, we'll elaborate more on that. And so based on historical data, the key summary statistic you extract is the sample size k hat is an integer. And then in the future, for a randomly chosen future question, you will use this sample size k hat for simulation, right? So suppose you already have 200 questions, and then for a new question, you will query the language model k hat times to get synthetic responses and construct a confidence interval. Your final decision would be something like this. So you will say between 15% and 30% of the population will choose a certain option. Yeah, that's a typical type of answer you may get. Yes. So you, from the historical data, you aim to learn a sample size, and this sample size is directly provides practical guidance for future questions. So you can imagine you have 1,000 questions. That's your question bank, right? But in real social survey, people are not willing to answer too many questions. So you may randomly select a small fraction. Let's say among your 1,000 questions, you select 200 of them and ask real people. Then for the rest of them, the remaining 800 questions, you can use language model. You can use language model equipped with the right amount of sample size. Okay, so here's how we do it. Suppose you get a lot of questions, and in the simple case, let's say those are just yes or no questions, and there are m of them, right? So if there are yes or no questions, you are interested in the population proportion of answering yes. So the true population proportions are denoted by P1 through Pm. Those are the parameters of interest, but you cannot directly observe them. So for these historical questions, you have human responses, right? Each question, there could be dozens or hundreds of human responses, and then at least you can construct point estimates. That is just your empirical average. So P1 hat through PM hat. These are observable. These are learnable from your human samples. And then you can use the LLM to replicate these studies. For question 1 through m, right? For each question, you keep querying LLM. You can query as many times as possible, right? You get a sequence of just yes or no answers, right? Each question has a sequence. You have many m sequences, right? And selecting the sample size means we want to understand when to truncate this sequence. If our sample size is 50, let's say, then we will truncate this data stream at around 50. Yeah. So this is the data. You have real data from human summarized into these point estimates and synthetic data from LLM. Okay. Then what should we do? So from the LLM, suppose you generate k simulated responses, then you can construct a confidence interval. There are lots of standard tools. You can use central limit theorem or Hofting bound, empirical Bernstein bound, etc. There are lots of useful bounds. So for every sample size k, you can construct confidence interval. And you have m questions, so there are m confidence intervals. And you can also change k because eventually we want to choose k. So k from small to large. Yeah, these confidence intervals can be anything. You can use many different approaches as long as there's a fallback requirement. So if you have no sample, then your confidence interval should just be the full space. Yeah, that's some convention. Yeah. And if you have k sample, you can use your method to construct a confidence interval. Okay, so eventually we want to choose a good k so that these synthetic confidence interval have good coverage over the red quantity, these true parameters, right? But you cannot directly tune that, as in in conformal inference, for example, or predictive inference. Usually you have some tuning parameter and you choose them so that you can, among your valid calibration data, you have good coverage, right? But here your target of your parameter of interest, the thing you want to cover are real parameters, and they are not directly observable. So you cannot directly use conformal inference to do that, right? And instead, we are going to use this point estimate as proxies. So we don't know whether we can cover the real parameter in red, but we do observe this point estimate in blue. So we'll check how many of these interval j can cover the point estimate p hat. That is something that's computable. So there's an interesting lemma, since that, suppose you have a question. Okay, of course, here we need to assume these questions are randomly sampled from a distribution. Then if a point estimate is covered by this synthetic interval with 95% probability, then I can tell you for a future question randomly sample from the same distribution, your interval will cover the truth with 90% probability at least. Yeah. So in the condition, this is just an assumption made on the empirical quantity, right? You want your synthetic interval to cover the point estimate. And you can approximate this because for each point estimate and each synthetic interval, you can check whether it's covered or not. And then if this sample size is good enough so that it maintains the required coverage assumption, then I can tell you for the future question, you cover the truth with desired probability, right? So it's a translation or conversion from coverage over the random estimate toward the coverage of the true parameter.
So do we need some assumption on the number of the number of humans?
Great question. Magically, we don't. Yeah, that's the most interesting part because in practice, in the data set we collected, the human responses are very heterogeneous. There are hundreds of questions, but some questions only have dozens of people who responded. Some questions have thousands of people who responded. So these point estimates, P1 through PM, are very noisy. They have different variabilities even. Yeah, that's very interesting. But the key insight is that these estimates are noisy, but they are still unbiased. Yeah, so that's why you can convert the coverage over the random target to coverage over the truth. Yeah. And also that's why if you want 90% coverage here, you need to aim for 95% coverage. It's not the same. There's some adjustment.
Yeah. I just want to know. That's fine.
Okay. Yeah. Okay. Yeah. So there's nothing mysterious about 90 or 95. If you want 1 minus alpha coverage, you just do alpha over 2. Yeah. So that's an interesting lemma, and so that will directly lead to our key method. So for every k, sample size k is the thing you want to select. For every k, you check among your historical questions how many point estimates are covered by your synthetic interval. So this is a fraction. And then you want to make sure this fraction is bigger than 1 minus, let's say, alpha over 2. Yeah. So you choose the largest k so that all of these fraction numbers are above that. Yeah. It's very similar to some hypothesis testing and false discovery rate control techniques. Yeah, so you choose the sample size k as long as you maintain some coverage guarantee. Yeah, so this method is implementable and very easy to run. So you choose a k hat now, and here's the theoretical guarantee. Okay, in the future, if you have a question from the same distribution, then you should use this k hat to generate synthetic response. Just generate k hat synthetic responses and construct a confidence interval as if you in the same way as you did before. Then we have the cover guarantee. Your synthetic confidence interval will cover the truth with at least 1 minus alpha probability. Yeah, there's some small term. Yeah, and you may wonder what does it depend on, right? So here essentially this small term depends on the number of historical questions, because you want if you have a huge number of historical questions, then this remainder term will be small. It's roughly 1 over square root m. Yeah, if you only have a few number of historical questions, then of course you cannot approximate very well. Yeah, but the most interesting thing is this assumption-free and model-free guarantee. It doesn't make any assumption on the fidelity of LM. Yeah, so you may have and come back to your point, you may not use an LM. You may use 40-year-old humans to simulate 9-year-old pupil. That's fine, right? So as long as you have some simulator, you can draw IID sample from the simulator, then this type of guarantee will hold.
Another question is, do you have some guarantee for the selected interval is just close to the one choice with optimal sample size with no P and Q?
That's a good question. Yes. So for Bernoulli, in an updated version of the paper, we do have such bound. Yeah, you can show it because we talk about the optimal sample size, the quote unquote optimal sample size. You can show for Bernoulli question, you can show this k hat is going to be somewhat proportional, at the same order of that. Yes. Yeah. So it does achieve.
And it's basically some assumption on the number of n or
no, still no. Yeah. Yeah, great question. Yeah. So in general, you cannot say anything about K except for this coverage guarantee because let's say you may have a bad LM, then the K will be small. If you have a good LM, this K will be large. But under more assumption, you can quantify, you can have more insights of K. Yeah. Great question.
So if we're not very difficult questions, then those questions need very large.
Yeah, exactly. So if you have heterogeneity among the questions, then so your quote unquote optimal sample size or fidelity will vary across the questions, right? But here the thing is that we are looking at an average case guarantee. So this coverage is not for conditioned on your question. It's randomized over your question. Yeah, so it's similar to conformal inference. You cannot make conditional coverage guarantee, but you can have an average marginal coverage guarantee.
I wonder what will happen if you consider there exists some very difficult question making K very large. Like K high because you take the largest one. But if you consider not taking the largest one, but with high probability it cover most of the questions.
Exactly. So you can definitely do that. And maybe another approach is that if you have a question of interest, then you can do a local version of this. You just look at other questions that are similar or comparable to this difficult question.
Okay.
Then you apply the same approach. Yeah, that could make it better tailored. Yeah.
Thank you.
Yeah.
So I'm sure if I understand correctly, but in the worst case, if we use the Bernoulli, the interval will be from just 0 to 1 in the worst case.
In the worst case, yes.
Yeah. So how can we avoid that, or it's unavoidable?
In general, it's unavoidable. Yeah, if you have just a very bad model. Yes. Suppose there's a model that always outputs yes. Right? Yeah, that's a very bad LM. Okay. I hope things are clear in the Bernoulli case, and then you can definitely generalize it beyond Bernoulli. Suppose you have general questions. The general question means their response could be numerical. Let's say you want to understand their income, people's income. You want to get the distribution, the income distribution in the population, right? Or the height distribution or weight or some numerical figure. It can also be a text response, right? In education, like GRE test, TOEFL, TOEFL test, right? You need to write some article. That is a text version. Yeah. So there can be general questions, and then for each question, there's still some population parameter of interest, right? It's not the Bernoulli proportion, but it could be, let's say, the average length of the response, or the median number, or 70 percentile of or some word frequency, etc. So suppose you have some true there for each question, there's a population parameter of interest. Right? It could be multidimensional. Those are not observable. You want to get insights about them, and you collect real human responses, right, for each question. And because the real responses are unbiased, you can use standard statistical tools to construct set estimates, right? Confidence interval, confidence set, or ellipsoid, etc. So use standard statistical methods. And because the human responses are real, they're unbiased. So these real set estimates have the valid coverage. You can choose the coverage level. Okay, then let's replicate those studies again using LLMs. If you generate K samples per question, you can construct these synthetic set estimates. And of course, you don't know how well they will cover the truth. You want to select the K just as before. So here's some guarantee. It's an extension of the previous results. So let's first assume the real confidence sets you construct have at least 50% coverage. Okay, you can definitely do this because the real data is unbiased. So there are statistical ways to do this. So suppose this is true, and then, okay, I want my synthetic interval to cover the real one with sufficient probability. I want my synthetic interval to cover the real one with 1 minus alpha over 2 probability. Then, if I use this sample size for future question, okay, I use this sample size, I can show my synthetic interval can cover the true parameter with desired nominal 1 minus alpha coverage. So ideally, you want the synthetic interval J to cover the quantity in red, this true parameter, but you cannot see them. You cannot directly check the coverage over that. So you resort to the proxy. The proxy here is the real set estimates constructed from the real samples. Yeah. So if your synthetic set can cover the real set sufficiently often, then your synthetic set can cover the truth. The true parameter also very frequently. Yeah. So yeah.
I have two questions here.
Right.
So in practice, we don't know whether I is included in J or not.
That's right.
In practice, like I can.
You would do the average. Yeah, you do the average.
I can regard this as like, let's split I into the part that is included in J and the other part outside J. Then this inside part guarantees this property and outside part. So we are maybe just unlucky.
Yeah, that could be one approach. So, but in many cases, for example, if I and J are intervals, you can check if one is contained in the other or not, right? If they only have some partial overlap, in our study we just discard it. We just regard that as a non-coverage. Yeah, here this containment means full containment.
One more question is about the number of questions. And does it play any role here?
So in this theorem it doesn't, but in the next few slides when I talk about our method, it plays a role. So your coverage eventually you will not get perfect 1 minus alpha coverage, but 1 minus alpha up to a small number. That small number is of order 1 over square root m.
And
So
there is a kind of multitask effect or something behind it.
That's right. That's right. Exactly. Okay. Yeah. So it's more beneficial to have more historical questions. Yes. Yeah. So practically, here's the method. You construct these real coverage, real confidence sets, make sure they have 50% cover probability. And then among your historical questions, you check how many real sets are fully contained in corresponding synthetic sets. Yeah, shorter interval contained in a longer interval, right? And then you select the sample size K. So eventually, here's the theorem. If you use our selected sample size K, then in the future, for future question, you can show the synthetic interval can cover the true parameter with almost 1 minus alpha probability. Yeah, that's the one I just talked to, discussed with Masashi. Here, there's a little error term that's decaying as your number of historical question grows. Yeah. So, yeah.
So it seems the theory for the one-dimension case and the multi-dimension case same. So is there some effect on the dimensionality?
Okay, so here there's no effect, but the difference lies in the your proxy. So in this multi-dimensional or general case, for the real data, we are constructing confidence sets. They are not just point estimates. Yeah, in one-dimensional case, especially Bernoulli or Gaussian some case, you don't need to construct a confidence interval or sets for human response. It can be just points. Yeah, but here you can see we are being more conservative. Yeah, for the real human responses, we want to provide some leeway already, and then we want to further let the synthetic set to cover this error bar. Yeah, that's the main difference. Yeah, but the guarantee doesn't have any dependence on dimension. Yeah. So some interpretations. The key. So our method is a key component of the method is this sample size k hat. Then you may wonder, what does it mean? Right? We know in Bernoulli case, the k hat represents some distribution shift between the real and synthetic distribution. But in general, can we have some interpretations? Right? So I would like to compare this with the very popular approach of parametric bootstrap. So just recall, in statistical 101, here's what we learned. In parametric bootstrap, you start from a sample size, a bag of training sample of size n, and then you feed a statistical model, denoted by the theta parameter. Right? This machine is your model. And with this model, you can keep sampling. You just simulate synthetic data. And in parametric bootstrap, you will use the synthetic data to construct confidence interval, confidence sets, etc. Right? And what should you do? Well, you'd use this to generate small bags of samples. Each bag is still of size n. The size n is the same as the size of the training sample. And you generate many, many batches. There's a tuning parameter b that's very large, a few hundred or a few thousand. So, but the key thing is that each bag only has n samples. That's the same as the synthetic the training data. Yeah. Here in parametric bootstrap, you are generating samples, batches of size n, because this n actually captures your statistical fidelity or accuracy. You can imagine if you use parametric bootstrap, but each bag, you're not generating n, but generating very huge number, and then you use those synthetic data to quantify the uncertainty. If each bag is too large, you will be overly confident. If each bag is too small, you're overly conservative. You result in a very wide band. The correct sample size is just the same as training. Yeah, you can view n as the amount of information you have from the distribution. Yeah. So in parametric bootstrap, you know how many samples you generate because you know how this model is trained, right? But in our case, the model is a black box with unknown training procedure. Just imagine ChatGPT. You don't know what type of data has it been trained. It must be a mixture of real data from the internet and also combined with synthetic data, etc. So it's a mixture. You cannot say the language model is trained on NIID samples. Right? It doesn't work that way. So it's a black box. Its model is already given to you with unknown training procedure. But still, we want to select a sample size. So it's like you still want to mimic the idea of parametric bootstrap, but without knowing the training process. So you have to learn some effective sample size and then use that to generate the downstream sample. Yeah, that's our approach. So we learn the sample size through the comparison between synthetic and real data and generate the synthetic samples. Okay. And here's a thought experiment. I find it pretty interesting and intuitive. So imagine your LLM is not a real machine. It's actually a room of real people. It's made up with a call center with n randomly hired human agents. Okay, and whenever you type a query, one of the agents will be randomly selected from the room and respond to it. Suppose the LLM works this way. Okay, I'm not totally joking because there are actually news reports, about some AI startup companies, several startup companies claiming they are using AI, but they are actually doing this. They hire people behind the scene. They're doing the lots of manual labors. Yeah, so you can imagine that your LM is actually such machine. And also, by the way, this is usually called artificial intelligence, because if this is artificial intelligence, that means it's a machine, but it's a fake artificial intelligence. So that's then you go back to real human, right? So A square I. So suppose this is your real language model, then what should you do, right? So you want to collect people's opinion towards something, but your room only has n people, and if you keep sampling from such LM, then you will get lots of replicates. There's a lack of diversity because if you draw too many samples, eventually you will see all of these people hidden inside the LM. And then after that, when you keep drawing sample, keep querying them, you get repeated answers, right? Or similar opinions. Yeah. So, for such a system, definitely there's no benefit in drawing too many samples. Roughly speaking, if your language model has n real people hidden inside, then you draw around n samples. Yeah, that's also the same idea with the same idea as the bootstrap. Yeah, for such a system, n synthetic responses would suffice. You can show, I think, come back to Yuji's question. In certain scenario, you can show our selected sample size is roughly proportional to this n, and that's the optimal measure of distribution shift. Yeah. So, coming back to to our method, we select a k-hat, and you can view this as an effective sample size and also a fidelity measure, because for this system, if n is large, that means your language model contains a huge population inside. Then your model has high fidelity. You can represent a huge population. If your language model only contains a few people, then it can be biased. So the k-hat will be small and your model has low fidelity. So you can view the k-hat as a fidelity measure. The higher, the better. And of course, if you have a perfect language model that's perfectly aligned with the real population, then intuitively your effective sample size will be infinity. Because if you really have a perfect simulation model, you should just simulate the infinity many times and get the population parameters. Yeah, but in reality, there's always a sim to real gap between your simulator and the real world. So your effective sample size will not be that large. Yeah, will be a finite number. And you just simulate until to the right amount. Okay, that's some interpretation. And finally, let's see a few numerical examples. Yeah, how large are those sample sizes? Okay, the first example is an opinion QA dataset. That amounts to public opinion survey. So this dataset consists of general US population responses to surveys on science, politics, health, and it was conducted by Pew Research Institute. In this dataset prepared by someone, there are all about 400 questions, and each question has 400 plus responses. Yeah, some of them even have 1,000 or tens of thousands responses. Some can be just a few hundred. Yeah. Okay, so this is a real data set. And let's see if our commonly used language models can be used to simulate such responses, right? How well are they aligned with the real human opinion toward these questions? So as a simple goal, here we choose to estimate every sentiment score of each question. Yeah, of course, you can apply it to general multidimensional parameters, but we just choose a simple illustration. The average sentiment score, because each question has has answer of different degrees. From typically you will say you totally agree, or somewhat agree, or you're neutral and totally disagree, etc. So there's some sentiment score toward each question. In our study, you can check more details in our paper. We use a fraction of those questions to learn the sample size and then test for coverage on the remaining questions. Yeah, so it's like a training and testing split, because we claim our synthetic confidence interval has some good coverage. Yeah, so we hold out some data to test for coverage, and in the paper we have rigorous statistical hypothesis tests for assuring this coverage. Yeah, but let's look at the most interesting part. That's the sample size k-hat. Yeah, so if you want to construct 90% confidence interval, here's the result we get. The best performing model is a ChatGPT 4.0 in our study. That effective sample size k-hat is about 60. So that means for this type of questions, social opinion questions, if you use GPT 4.0 to simulate the general US population, you can simulate 60 times. And then just construct a confidence interval. That error bar will be valid. Yeah. And for other models, they have smaller sample size, and as a result, a wider confidence interval and more variability. Yeah. So, for example, this llama is the next performing. These methods are similar: Cloud, Mistral, etc. And we also included a random baseline. That means you just do a coin flip. Okay, so you have a bunch of choices, and this random baseline just randomly picks one response uniformly at random. Yeah, you can see that random baseline has effective sample size 18. Yeah, here for a sample size of this, in our experience, it results in very wide confidence interval. It doesn't. It's not informative, and that's understandable. So all of these models we tested are much better than random baseline, at least. So in the opinion QA. And there's another example, numerical example we tried on online education. So these are student responses to multiple choice math questions, just like the one I illustrated at the beginning, right? Those are multiple choice questions for elementary school and middle school students. There are 400 questions in total, and each of them has a variety of student responses, and you know the features of the students, etc. Yeah. So here the goal is to estimate students' answering accuracy of each question. Yeah. So this will be very informative to the instructors, right? The teacher who are interested in learning this. And also, of course, you may ask other questions. For example, there are A, B, C, D choices. In addition to just estimating the accuracy, right? How many students can make the correct choice. You may also want to get common mistakes, right? What is the most misleading choice? What is the most confusing point to the students? You can ask those interesting questions. Yeah, as long as you have a good simulator. Yeah. So it turns out for this one, the results are far from being satisfactory. All of the models we tested have pretty low effective sample size. Yeah. And so the first tier of models have sample size around 8 or 7. And even the random baseline, which means you have A, B, C, D choices, and this random baseline just randomly picks one. This one has 7 effective sample size, and all of them have very wide confidence interval. Yeah, it's not for this task. The models are not ready to be deployed. They still have very low fidelity in mimicking student behavior. Yeah, and also a few models are not significantly better than the random guess. Yeah, so we see we do verify, we do look at the bias in this model. It turns out all of them, all of the models tend to think that students are very smart. So they are good at selecting the good answers. But if you really want to simulate student behavior, it's a different question. Yeah, they are biased upward in the answer accuracy. Yeah. So just to summarize, here in this study, we consider how you can reliably use large language models to simulate survey responses. We provide a method that can select an effective sample size with nice interpretation and also valid answer quantification. Yeah, the method comes with a model-free guarantee. It's easily applicable. Our paper is available on arXiv and also just accepted on ICML. Yeah, and that's all I want to talk about today. And thank you for those nice interactions, nice questions.
Yeah. Thank you, Kaizheng. So for the next talk. So do we? Oh, yeah.
Thank you for a great talk. So I have a question. Like I saw your experiments just to use the the basic LLMs, but the whole process I think is actually a very good COT chain of thoughts, and would it be better to or meaningful to use all of these experiments as some kind of templates or chain of thought to train a good reasoning model?
Yes, I think so. So currently, even if you use the same approach but apply to more advanced reasoning models with chain of thought, we do see some improvement because those models, through the chain of thought, they can better reason about humans' behavior and they can predict better accuracy. Yeah, we do see the benefit. And also you can, as you said, you can integrate this method and let's say integrate as some part to steer and guide the chain of thought to achieve better alignment. I think that could be possible.
I see. Thank you. So I have another question, like if your experiments is multi-turn or just one turn each time.
What is multi-turn?
I mean, because it's like a QA, right?
Yes.
So is it a multi-turn or one turn?
In our method, in each query, we just simulate one person and one question. Yeah, and then we repeatedly do a for loop to this.
I see. So each question is independent. Right?
That's right.
I
Each
see.
question, each response is independent.
I see. Thank you.
Yeah.
Wonder you mentioned simulating demographics very early on in the talk.
Yeah.
Is it easy to simulate demographics, and is the subsequent result actually a simulation of different people?
You mean these features, right?
Also students.
Yes, students. Right. So there are some other studies showing the language model has different fidelity toward different demographic groups. So definitely these features matter. Yeah. But in our study, we didn't look at a fine-grained structure in each small section, but we just borrowed the same. You can think of we are using the same composition of the population as in the real data. Yeah, we are not distinguishing. We are not focusing on each particular group.
In your IID simulation run, do the prompt change from one?
We don't. We use the same prompt. Yeah.
Do you tune the temperature?
I didn't. So we just borrowed all those configurations from some existing work. Yeah, to make things simple. Yeah, but I think that could make better because by tuning those knobs, you can perhaps achieve better alignment.
Yeah, thank you very much for the great talk. I have a few random questions.
Okay.
Like here, what happens if you directly ask LLM to give us a kind of distribution?
Oh yeah, great question. So we tried that. So for example, here you have 5 categories. So you can directly ask the LLM to give these 5 probabilities, right? I think very interestingly, that turns out to be better than this approach in some cases, but it's not uniform. In some cases, I think in education data, that's better.
Can you somehow leverage that kind of property in the proposed algorithm?
Yes, yeah, you can. For example, for example, you can first just ask the LLM to generate a distribution to predict these 5 to predict whole distribution, and then you may further sample from the distribution, and then get the idea is to get some error bar around that distribution. That could work. Yes.
Another question is, so nowadays we have a lot of different LLMs,
Yes.
and maybe one is quite good and maybe others are like reasonable, for example.
Right.
Then, like, is this diversity help in like predicting better?
Right. So
if you have a like super very good LLM, single LLM, then do we depend on this?
Right. So I think currently we tested on a bunch of LLMs, and I think for in some cases one GPT-4o is dominating the others in this public opinion, then you can just use that. But we do observe there's heterogeneity in the performance across different questions. So in some type of questions, this LLM is better. In some type of questions, the other LLM is better. So they vary. You can view it as a mixture of expert problem. Yeah. For every given question, there could be a best performing LLM for that question. So ideally, you may want to, if you have a bunch of LLM, you may want to select the best one for each question or do a mixture of the response. Yeah, that would be a great question. So far we've only been considering any given single LM. Yeah, but I think that should be the something to look at.
Okay, thank you very much.
Yeah.
Is there any other questions? Check the online chat box. Okay, it seems